Hello everyone, I welcome you in this YouTube video lecture. In last lecture, we have discussed successive approximation type register, analog to digital converter, and in this type of ADC, we have seen that the conversion time is independent of the applied input voltage and it always equal to the number of clock pulse applied or the number of successive approximation register or ring counter we have used. In this lecture, we will discuss about the flash type ADC, flash type analog to digital converter. So let's start with the flash type analog to digital converter. So if there is n bit converter, then minimum 2 raised to power n minus 1 comparator we need to construct this circuit. 2 raised to power n resistors we have to use to provide reference voltage to the above comparators, and we also need a 2 raised to power n cross n priority encoder to provide binary numbers. So in a flash type ADC, number of comparators are connected in parallel to increase the speed of operation. Hence, it is also known as parallel comparator type analog to digital converter. So, in this figure, a 3-bit flash type analog to digital converter circuit is shown. So, for a 3-bit flash type ADC, you can see there are 8 resistors and 7 comparators, and 2 raised to power, according to 2 raised to power n cross n, a 8 cross 3 priority encoder is used. The one input of all the comparator is the applied analog voltage, and the other input are at different reference voltages. So you can see that if the applied voltage is VR or the reference voltage is VR, then the second input of first comparator is 7 VR by 8. Similarly, second input of second comparator is 6 VR by 8, and if we calculate according to this, then the second input of last comparator is given by VR8. Because this 2 raised to power n resistor make a voltage divider circuit, and this VR reference voltage is equally divided between these 8 resistors. So the resolution or step size of this type ADC is given by V range upon 2 raised to power n, and this is 8 cross 3 priority encoder whose input are the output of this comparator and the output is the converted binary. So let's see how this flash type ADC work. So let reference voltage of the above circuit is 1 volt, and we want to convert 5.3 volt into digital voltage. Then this is the output of priority encoder, where Y0 is the LSB and Y2 is the MSB, and this is the range of the analog voltage. So you can see if the applied analog voltage is less than VR by 8, Then all the comparators output are 0 and the binary output is given by 0 0 0. Similarly, when the applied voltage are in the range of VR by 8 to 2 VR by 8, then the last comparator output is 1, and according to this combination the binary output of priority encoder is given by 0 0 1. Similarly, you can see for 5.3 volt it comes in the range of 5 by 8 to 6 by 8, and when this combination is occurs, then corresponding to this combination the output of priority encoder is given by 101, and this is the binary equivalent of the applied voltage. So there are total 8 combination, and according to that 8 outputs are possible for 8 to 3 binary priority encoders. So these are the advantages of this ADC. Flash type ADC is the fastest ADC because it parallelly compare all the possible formation of input, and the maximum number of clock pulse for n-bit conversion is only required only 1 clock pulse. The disadvantage of this type circuit is that it requires more hardware, or the circuitry is the complex. That's all for today's lecture. In next lecture we will discuss dual slope integrating type analog to digital converter which overcome the above disadvantages. Thank you.